our mass spring chain. And I think I should actually write the diagram up. I'm going to do my best to draw straight lines with reference to the coordinate axes that are given to me by the engineers of this board. We'll call this position right there x sub 1, and we'll call this position right there x sub 2, and we'll say that we start this at the initial time 0. What is x sub 1 again? Position of the center of mass at equilibrium, which means 0 velocity, 0 acceleration, 0 net force, right? These scalars, many of you thought about these as algebraic scalars. The scalars k1, k2, and k3 are solutions to what you might call differential problems. They're least squares problems. We haven't actually talked about how to construct that yet because we haven't learned least squares. For now, we're going to assume that people just give us these, the manufacturers of the spring. Has anybody ever tried to build a spring out of wire before? It's not easy to do. It's not an easy problem, let alone figure out what the spring constants are. But for now, you can think about those as constants. They're given constants. In lesson 22, these will be the solutions. They will be output by a least squares problem. So when we solve a least squares problem associated with the particular Hooke's law experiment, we will produce differential solutions to an algebraic problem, which happen to give you what these are, right? And that's exactly what the manufacturers do when they construct this. What's going on over here? The whole paradigm here was that we turned off gravity. We let the things come to an equilibrium position in a static paradigm, right? I would like to now allow time to be variable. So we are actually going to do this derivation from the standpoint of dynamics. This is going to be a differential calculus derivation, not an algebraic derivation. Meaning to say, do you remember when we first worked on this problem and I brought that board with me to class? When I looked at the second case that I turned gravity on and we actually mapped the location of the center of masses, were those masses moving? No. Today, we will allow for the option that the mass moves. When we derive this thing, we will say these masses are allowed to be in motion. Give myself a solid. In that situation, do you remember what we called the location of center of mass 1 at time general t? x1 of t. Do you remember what we called the center of mass 2 at time general t? And then we had this idea that we could actually measure the distance between the two of those things. If I said that the ruler had ruler ground up here and positive direction went down there, positive position measurements would happen in the downward direction. In that situation, we might say that let's go ahead and think about positive displacement as happening in the downward direction. What did we call the difference between the initial and any point? u1 of t. In this case, that was the displacement function. How would I calculate that? Well, it's the final position minus the initial position. And that immediately implies, when is u1 of t positive? Well, that would mean x1 of t is greater than, x1 of t minus x1 is greater than 0, which would mean that the position of the mass is farther along the ruler. What does that mean in terms of the orientation of my apparatus? That mass would actually be below its starting point. It would be closer to earth ground, right? Farther away from ruler ground, but closer to earth ground. Could you then imagine what we say U2 is, besides a band that makes money on... What is U2? It's the displacement of mass 2, and this thing is now what we might say is x2 of t, the position of the center of mass at any time minus the initial position. When is that thing positive? when the mass is below. When are those negative? When is the displacement function associated with each of the individual masses negative? When it's above. And that can happen, right? If it's moving, the things can go up and down. I wish I had my little mock-up of this so we could watch the positive and negative happen. So let's go ahead and look at x naught as the vector of initial positions, and we'll look at x of t as the vector of positions of each center of mass at time t. What does that immediately mean about u? Say, it means I am super engaged. What do I owe you for that? What is u? How do I form u as a linear combination of these vectors? It's the position of all the masses at a particular time minus the initial position. This is a vector valued equation because it actually stores all of the displacements at once. The next thing that I want to do is start to analyze some of the dynamics of that system by looking at the individual physics for each component. We're going to create something called the elongation vector. And we're going to look at this for all three springs. So we'll start with spring 1. And we'll say t equals 0, and then this is a general t. At t equals 0, what happened? So my mass had position what? What was the position of the center of mass 1? x1. At general t, and we're assuming, let's assume for a moment that the spring actually stretches a little bit, but it doesn't have to stretch necessarily. What is the same position, or excuse me, the position of the same mass? It doesn't necessarily have to be lower, right? If this thing moved up, it could be this way, right? But what do we call that position? x1 of t. So now I'm going to go ahead and introduce what we call an elongation function. This is the amount of net, this is a very important word, stretch of spring 1. Oh, I'm so happy you do this. In this case, is it any different? No. So in this case, you made a very beautiful observation. That's a silly definition, Jeff. Let's get to spring 2, shall we? Two steps ahead of your teacher, 3 steps ahead of the class. Please stop singing, Jeff. Let's take a look at spring 2. What was the top end of spring 2? What's the top end connected one to? Mass 1. And that top end sits at the beginning if we have time equals 0. So that sits up there. And then spring 2 is kind of just chilling like a villain. Here's spring 2. And then what's the bottom end of spring 2? Mass 2. And where does that happen? x2. And then when we look at the general t, what happened to mass 1? So mass 1 dropped. By how much did mass 1 drop? So the amount that mass 1 dropped was u1 of t, right? And then maybe this thing actually stretched out a little bit. So the spring could have actually stretched out a little bit. How much did mass 2 drop? Yeah, so this thing dropped u2 of t. Let's suppose for a minute that mass 1 had 0 displacement. So mass 1 was fixed. How much would spring 2, if we think about this as the elongation, the amount of net stretch, and it is a net observation. This is not a absolute 0 observation. This is non-Newtonian. This is more relative, right? The amount of net stretch of spring 2 at time t. If mass 1 did not move at all, then this would be U2, except what happened to the top end of that thing? It dropped. So away from U2, you would take U1. Okay. Is there a difference between displacement and elongation? What's the difference?
We need to account for the displacement when we think about elongation.
And in fact, this is why I say that Hooke's law is ridiculous, because formally speaking, Hooke's law is about the elongation of the spring, not the displacement. Physicists say they're the same thing, but they don't actually necessarily say because the top end is fixed and thus the displacement is in a framework where the initial point is always the same. Hooke's law is formally about elongation, not about displacement in a frame of reference. The moment you fix that top end, then everything is cool. And they say that out loud, but then they don't actually go to the place where the top end of your spring might be moving, right? In which case that calculation is a little bit different. What's the last spring that's in this system? A3. So let's talk about spring 3. And we're going to have the t equals 0 paradigm, and then we'll have the general t paradigm. If the t equals 0, the bottom end of the spring is fixed. I don't know, I give myself a solid D+ for my springs today. What happens at the general t? Assuming that the mass traveled down, what happened to that spring? So this K2, same exact spring, K2, what's the displacement there? Yeah, this particular one would be U2, except when we're thinking about E3 of t, this is going to be the elongation of spring 3. And that's a net elongation at time t. When is elongation positive? When do you say that a spring gets longer? When it was longer than it originally was. This spring, under this paradigm, did it get longer or shorter? Did it have a positive elongation or a negative elongation? It had a negative elongation. This is what we call the negative of the displacement function for U2. It must be that way. U2 is positive, for sure. When U2 is positive, what happens? This is where I need my freaking springs, right? This is where I need I didn't bring them today. When U2 is positive, think about what that means. What does it mean for U2 to be positive? It means the mass went down. What happened to the spring at the bottom? It negatively elongated. In other words, it compressed. And how much did it compress by? The exact amount that the mass displaced. When U2 is negative, that means the mass went up. How much did it elongate? By negative U2. Thus, we now have a new vector, which we're going to call the elongation vector. Can you guess what we're going to look at that thing? This will be E1 of t, E2 of t, E3 of t. What are the different components of that thing? Look at the elongation of spring 1 was U1. The elongation of spring 2? U2 minus U1. Elongation of spring 3? When we're creating a model, are we doing it column by column or entry by entry? The actual modeling problem here, did we do these all at once or we do them separately? Entry by entry usually occurs when you're doing a modeling construction problem because you're literally filling in every single element of the model individually. And this is quite human. Modeling problems are quite hard, so you know what we do? Chop them into the component pieces, analyze each piece individually, then come up with a mathematical description of that. After we've done that, we are now in the mathematical analysis piece of this. Do you see a way to rearrange these sums to write it as a linear combination? And I'll give you a major hint on this. Do you see a linear combination with scalar coefficients? Maybe I need to go a little slower because some of you are not used to doing this yet. Anybody see a scalar that you can pull out? At any one point in time, what type of object is U2? Scalar. The whole thing, U2 of t, is actually what we call a function. But if you pick a single point in time, that function outputs what type of object? Scalar. Do you see a matrix vector product? Here we go. E of t, we just said was going to be u1 of t multiplied by 1, negative 1, 0, plus u2 of t multiplied by 0, 1, negative 1. Now I have a linear combination of the columns of a matrix with scalar coefficients coming out from a what's the whole idea of column partition version of a matrix vector multiplication? Linear combination of columns with scalar coefficients coming from the rows of a scalar. What are the columns of my matrix? You tell me, where did I get these from? Where did I get the positive 1 right there? Where did I get the negative right there? From her question. What's the difference between elongation and displacement? Right? Displacement is raw change in length. Elongation is raw change in position of the masses. Elongation is how much does that actually affect the change in length of my spring. And from that standpoint, that middle spring, the bottom end went down U2, the top end went down U1, so the difference in length would be the U2 displacement minus the U1 displacement. There's that minus, right? I mean, have I done anything? Do you agree with you that I can I add 0? Why can I add 0? Because it doesn't do anything. That's called the additive identity, right? Why can I switch the order of operations and pull off the negative? Called algebra. Can I add 0 there? The moment I've done that, would you agree that I can pull those into two separate vectors? Yeah, it's called vector addition, right? Once I have those two separate vectors, would you agree that at any point t, this thing is just a scalar? So then I can pull, if I have a scalar times this and a scalar times this and a scalar times that, can I just pull that scalar out? What vector arises? Once I have that vector, and I think about that as a scalar, and I have this vector, and I think about that as a scalar, what do I get out? Scalar times column vector plus scalar times column vector. I've erased the board. Do you have a paradigm in which you take a scalar times a column vector plus a scalar times a column vector and you add them together? What's that called? Linear combination. What's another way to realize linear combinations? Oh, I'm sorry. To actually understand what we're doing in a matrix algebra class, we have to actually string together all of my operations and be able to pick them off at will from an actual modeling context? Yeah. Welcome to applied math. Yep. That was not to you all. That was to every teacher that I ever had, right? Yeah.
So what we're doing is what we call we basically taking the whole change that happened from M2 initially and then where we at right now.
Yeah, we're looking at the way, how much do these springs change their length? How much did they elongate? Positive elongation means that the spring started here and it went there. Negative elongation means the spring started here and went there. You might call that stretch or compress. But I want to come up with a function to describe that. And I want to make sure that that function doesn't abuse the word displacement. Displacement has to do with the position of the masses. Elongation has to do with the change in length of the springs.
For the matrix vector multiplication, can we actually multiply them?
Did you need me to answer that question? Every single time you write a matrix operation down, what do I want you to do? The moment you do that, if you don't do that, I should be fired. So I just lost my job. Because you made me do it, right? So don't fire me. I want to keep my job. I want to keep feeding my sons. They're really important people.